We should be good to go here. All right. So let's say we're generically talk about. I'm going to give you a rational function, and we're going to define that rational function as p of x over q of x. All right. And that's going to be sort of the polynomial divided by a polynomial that we've sort of discovered before. So how do we find the vertical asymptotes? Well, what we discovered is that we set the q of x equal to 0, and then we solve. All right? So this part right here is how we find these vertical asymptotes. We're going to set q of x equal to 0, and we're going to solve. So as an example, if I gave you a rational function, r of x equals 1 over x plus 3 squared. Hi, CPU. Thank you. Got it. I would set the denominator, the q of x part, which is plus 3 quantity squared, and I would solve. Well, that's pretty easy to do. So that just means x plus 3 is equal to heads. So that means that x must be equal to negative 3. So x equals negative 3 is my vertical. What is my domain for that particular function? All real numbers. Good. So are you realizing that there is a connection between the domain and the rational function? The vertical asymptotes from a rational function? Hopefully you see that there is a definite link there. Right? What if... let's talk about this one. Find if I give you r of x is equal to 3x over 2x plus 1. Find the domain and the vertical asymptote equals negative 1/2. Okay? So hopefully you're realizing that there is a connection between the domain and the vertical asymptotes of a rational function. Are you guys feeling pretty good about that one? Yeah. All right, sweet. Let's get on to something that we haven't talked about yet. And let's talk about horizontal asymptotes. All right, horizontal asymptotes. I have to introduce a new vocab word before we can talk about horizontal asymptotes. And the vocab word that I need to introduce to you is this idea of what's known as a proper rational function. So, proper rational functions. Here we go. All right. The definition for a proper rational function says that if I have r of x, which is equal to, polynomial over polynomial, p of x over q of x. If the degree of p of x, which is the numerator, is less than the degree of q of x, which is the denominator, then it's a proper rational function. So let me give you some examples of what I mean by a proper rational function. This rational function, r of x, which is equal to x over x squared plus 1, that's a proper rational function. The reason is because the degree of my numerator is 1, the degree of my denominator is 2, the degree of the numerator is less than the degree of the denominator, therefore it's proper. Can you guys give me another example of a proper rational function? Can you make one up real quick? X squared over x cubed. Very good. That's a proper rational function. Can you give me two more? Good. Okay. X to the fourth over x to the fifth. Also proper. Of x equals x to the 10th over 300. That's the ones you made up. All of those are proper. Okay? You guys understand what proper is now? Now here's the cool part. If r of x is proper, then it implies I equals 0 is the horizontal asymptote. How crazy is that? Implies. That means it guarantees that it will be. Yeah. No. Implies means that this happens, then therefore this will happen, right? Yeah, Rachel.
So in simpler terms, if the degree of the numerator is bigger than smaller than the degree of the denominator, then your horizontal asymptote will be 0.
The line y equals 0. Yes. Yeah. Absolutely correct. Hey, you guys, is there another name for the line y equals 0? The x-axis. Very good. Okay. So let me demonstrate this for you. Has everybody got this down? No, you don't handle it. Okay, there's line y equals 0. So you notice that it's acting like a horizontal asymptote, right? And is that function proper? Yes, it is, right? So even if I make this a 13, okay, notice it changes the function, but it's still a horizontal asymptote, right? What if I make this a 12? Is that still proper? Yes, it is, right? And it's still a horizontal asymptote. Well, that seems kind of funky right there. So I take it away. It's still proper, right? Still good to go. Even if I have, like, I don't know, 131 or something, 131 all over 132, it still becomes the line whenever it adjusts there at some point. Does it work? Oh, no. Q of x. So these are our two scenarios if r of x is not proper. They're either going to be equal, or the degree on the top is going to be greater than the degree on the bottom. So as an example, right, for this one here, let's say I gave you r of x is equal to, let's do 10x plus 1 all over 5x plus 3, okay? First of all, why is this not a proper rational function? Because the degrees are the same. Okay, good. So what I want you to do is I want you to graph this function in your calculator right now. 10x plus 1 over 5x plus 3. So in the calculator, we'll bring this up. Go y equals. It clear this out. Clears out. Okay, you have to put these in parentheses. Plus, ooh, someone notices something. Divided by 5x plus 3. Okay? So when you hit graph, make sure you have them in parentheses there. And when you hit graph, you should see this. Now, we're still talking about horizontal asymptotes here. We already know the vertical asymptote will be at -3/5. We know that one, right? Because we just look at the denominator and go for it. But do you see that there is a horizontal asymptote there? I wonder where it is. Parker, where is it? It's the line y equals 2. So let's go down here and graph the line y equals 2. And when you do that, you should see that. Now, Parker, how did you know it was the line y equals 2?
It's the ratio of the leading coefficient.
Yes, very good. He said it's the ratio. Check it out. 10 divided by 5, how much is that? Holy cow. Y equals 2 is the horizontal asymptote. So if the degrees are the same, you take the quotient of the leading coefficients. And you get the horizontal asymptote there. That is crazy. That is crazy that that's what it is. Now, the other option is, okay, if the degree is bigger, this is called an oblique asymptote. And that's where we're going next. Have you seen this lesson before?
Yeah.
Where?
I have
Oh, sweet. Good. I love it. So then you're right on board, right? All right, so box number 4 is talking about oblique asymptotes. So an oblique, what's the sorry, do you guys know what oblique means? Diagonal, right? Yeah, this is a slanted line, right? Some kind of a line, right? And it could be slanted line means slopes could be up, they could be down. They don't have to necessarily be diagonal, but it's just an oblique is a fancy word for a slanted line. So now here's the disclaimer, okay? Yeah, I can go right to there. All right, here's the disclaimer. You can only have oblique asymptotes. Only have oblique asymptotes if the degree of P of x is greater than the degree of Q of x by exactly. So there's your disclaimer. You only get oblique if the degree of your numerator is greater than the degree of your denominator by exactly 1. Otherwise, you get a quadratic if it's a difference of 2, which quadratic asymptotes in this class. So, for example, OB stands for oblique, yeah. So if r of x was equal to, I don't know, let's do x squared plus 2x plus 1, all divided by x. Yeah, let's talk about it for just a second, right? X squared plus 2x plus 1 over x. First of all, we have a rational function. Where would the vertical asymptote be? No, where the vertical asymptote be? X equals 0. Very good. Nice job, Rachel. Where is this a proper rational function? No, why not? That's right. The degree on the numerator is a value of 2. The degree on the denominator is a value of 1. What's the difference between those two degrees? 1. So therefore, we're going to have an oblique asymptote. The question then is, how do we figure out what it is? And we use long division to do it. Very good. So because we have this, we know we're going to have an oblique asymptote. And the way that we get it is using long division. All right, so we're going to actually do that right now. So we'll take x squared plus 2x plus 1, and we're going to divide it by x. And we're looking for the equation of a line up here in our quotient. And once we get that quotient, we can stop. And then we'll graph it and do a little analysis. Okay, so how many times will x go into x squared? X times. Very good. This is a great application for long division. So x times x gives me x squared. I'm going to draw a line. I'm going to subtract. Nothing by design there. That's easy. Then I'll bring down x. Will x go into 2x? Yeah, because their degrees are the same, right? How many times? Plus 2 times. Good. You can stop right there. That's all you care about. So therefore, through long division, the line y equals x plus 2 is guaranteed to be the oblique asymptote for this rational function right there. Because we're only looking for the equation of a line, which is in the form y equals mx plus b. Because after all, it's a slanted line. So as soon as we have that line, we're good to go. We don't need the remainder or anything else. Okay? So let's graph these in our calculators and see what's going on. So make sure you put the numerator all in parentheses, all right? So we'll go parentheses, x squared divided by x. And then I'm going to get rid of everything else. I will in a second. I want everybody to see it without it. So you should get something that looks like this. Crazy looking, right? You alright? Hang in there. It's weird, right? It's super weird. But do you see how there's no horizontal asymptote? Right? But there is a vertical at 0, and there's this oblique one. It looks like it's slanted, right? So let's go back and let's put in the one that we found by x plus 2. So we'll go x plus 2. Boom. And you should see that that goes right in between there. So I think the one I had is, no, where is it? No, I'll make another one. So the equation was, what is it? X squared plus x plus 1? Is that what it was? Did I do that right? Or was it 2x? Isn't it funky? All over x. Yeah, it's all mad at me now. Yeah, my computer's almost out of memory. So I gotta get a new one. Alright, so when we graph this thing here, we should see this. Yep, there we go, that's good. Okay. Now, we came up with the equation y equals, what was it, x plus 2? Okay. There we go. Catch up. There he goes. Good. So when I graph this on the line, you can see that the oblique asymptote, so it all behaves the same. Ready? I need all this time. Okay. Here we go. We are going to graph a rational function by hand. I am going to lead you through all the steps.
Why are you scaring me?
Because Seth is making me laugh. I'm going to lead you through all the steps, all right? And we're going to have a great success, and then we're going to actually see our answer match what's on the calculator. Yes, I love the enthusiasm. Okay. Okay, number 1. The first thing we're going to do is we're going to get the domain. All right. How are we going to get the domain? Yep. So, well, the domain for us is just all real numbers x such that x is not equal to, what are the two values that would give me a 0 in the bottom? 0 and negative 4. Very good. Hey, step 1 done. Easy. Okay. Step done. Number 2. We are going to find the x-intercept. Now, how do you find the x-intercept of... Yeah, you set the numerator equal to 0. So we're going to set p of x, right? Because after all, the top part represents p of x. The bottom part represents q of x. The definition. Equal to 0, and then we're going to solve. So, here we go. X plus 1 equals 0. That's easy. X equals negative 1. Awesome. Step 2 done. Okay. But there's only 6 steps. Yeah, we're doing good. Yeah. Okay, number 3. We're going to find the y-intercepts. Now, how do you find y-intercepts of a function? Yes, perfect. You set x equal to 0, and you solve. Okay, that's going to look something like this. 0 plus 1 over 0 times 0 plus 4. That's equal to 1 over 0. That's equal to calculus. So, for us, that means there's no y-intercept. Sweet. No y-intercept. In calculus, it means something totally different. That's going to be a lot of fun. Okay, no, it's actually really cool. It's actually really cool. Okay, step number 4. Don't lose focus. You're doing great so far. Step number 4. We're going to find the vertical asymptotes. Well, that's pretty easy because that's related to the domain, isn't it? It's the same thing. So the vertical asymptotes mean, there's going to be 1 at 0, and there's going to be 1 at negative 4. Perfect. Good. I'm glad to hear it. Step number 5. When does it get bad? Step number 5. We're going to find the horizontal asymptotes. Well, that's pretty easy too. Because what type of a function is this? It's no rational, which I guess ratio kind of goes in there. Is it proper or not proper? How do you know it's proper? They do not have the same degree. Very good. The degree of the numerator is what? This is a degree equal to 1. And what's the degree of the bottom? 2. So therefore it's proper, right? So it's proper. So that means that y equals 0 is the horizontal asymptote. Oops, I don't want black there. Okay, step 6. We're going to find the oblique asymptotes. Yes, very good. Now, if there's a horizontal, then you're not going to have an oblique. So there's none for us. You can only have an oblique and horizontal. You can't have oblique and horizontal at the same time. Okay? All 6 steps. Now we got to put it all together in a graph. Okay? So give yourself some space down below. Give yourself some space. Use your inspirational straight edge. Very good. There are none. You guys good? All right, here we go. Let's go back to the very beginning here. Let's start reading off some information. We know the domain is everything except for 0 and negative 4. Good. We have an x-intercept. Where is the x-intercept again? Negative 1. So when x is equal to negative 1, I'm going to have an intercept there, so I'm going to put a little dot there. Number 6 was the oblique asymptotes, and in this case there are none because the function was proper. All right, next thing. Where's the y-intercepts? 0. Nope. We do not have any y-intercepts. We're good to go. Where are the vertical asymptotes? 0 and negative 4. So at 0, I'm going to put a vertical asymptote here, and at negative 4, I'm going to put a vertical asymptote here. And I'm going to label those. This is the line x equals 0. This is the line x equals negative 4. Please label those. Huh? Hold on. Good on the list. Do we have any horizontal asymptotes? Yes, we do. What is it? 0. Don't say 0. Say something more precise. The line y equals 0. Thank you. There we go. So that would be this line right here. And it's the line y equals 0. And I'm going to label it just like that. Okay, now, do you see that we have split up our graph here, or our coordinate plane, into 4 regions? Okay? I'm going to highlight the 4 regions for you, okay? There's a region over here that's to the left of the asymptote. There's a region that's in between the asymptote and the intercept right here, okay? There's also a region that's in between the intercept and the other asymptote here. And then there's a region that's highlighted over here to the right of the asymptote. Do you see the 4 regions? They're highlighted for you, okay? So those are the 4 regions that I'm talking about. I'm going to erase them because we're going to talk about them right now, okay? Please erase. Please erase. There you go. Boom, 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 and boom. Okay, good. So now, in the region on the left here, all right, my graph is doing one of 2 things. It's either looking like this or it's looking like that. I know that is because I have boundary lines that are asymptotes. So as my line goes out further away from x, it's going to behave more and more like y equals 0. As it gets closer to x equals -4, it's going to shoot up to infinity or down to infinity. But I don't know which one it is, okay? So I have to do something about that. In this region, it's doing the same thing. It's either coming down and going this way, or it's coming down and going up, or it's coming up and going down, or it's coming up and going through. So I have all these regions here, and I don't know exactly what it's doing, okay? And then likewise for that 3rd region. So what do? Well, this is what we do. We use the table, and we plug our calculators in. So take your calculators out, and plug in the function as it would think it was +1. Yes, you do. Divided by parentheses. I'm going to call this x squared plus 4x. And the reason I'm doing it that way is because I just distributed that x in the denominator to write it easier in the calculator. Okay? So I'm going to say x squared plus 4x. Now, we're not going to hit the graph button because we could, and we're going to save that for the end to validate our work. Instead, we're going to go to the window. So second window, which gives us to the table setup, right? Second window is the table setup. Make sure that your independent variable is set to ask. So go down, highlight ask, push enter 1 time. Once you've got this set up, go back to the table. So second table. All right. Doesn't matter what you have in there. Okay. What I want you to do, though, I want you to give me an x value that is in the region that's to the left of -4. Oh, -5 is, right? What's the output when x is -5? That means that my function has to be where? That means it has to be below the x-axis. Like that. Okay? Now, whoa, just cracked. Been talking all day. Now, yeah. Give me a point that's in between the asymptote and -1. -2. Check it out. What's the output when it's -2? So is that positive or negative? It's above, right? So therefore, I know that my graph has to be doing something like this. Has to be above it because it was a positive output. Now, I need to test the region here. What's in between 0 and -1? -0.5. So when I test -0.5, whoa, where'd you go? What'd you guys get? I get -0.28. So that means that it has to be below the x-axis. So that means the only thing it could be doing is crossing there and then shooting downward to infinity like that. Okay, and then finally in the 4th region, give me a point that's in that region over there somewhere. 1. Okay, good. Check it out. 1, 5, 7, doesn't matter. If I plug in a 1, I'll get something positive. Plug in a 5, I'll get something positive. 7, something positive. I'll get positive values everywhere. So that means it's above. So the only thing my function could be doing is doing something like that. Now you have earned the right, you guys. You have now earned